Hey, it's me, Steve. Welcome to my new series. This is going to be called the Geo-Files. This is the very first episode, and I'm going to talk about reading geologic maps. Reading geologic maps is important. It's not just of academic value. You can use a geologic map to give you an idea of where to find economic resources, including groundwater. But before I get into any real detail about geologic maps, like the one up here you see of northern Wisconsin in the western part of the Upper Peninsula. This is a bedrock map. You see over there are cross sections. I'll get into those later. And here's a bedrock map of Illinois. I'm just going to have to give you some background on maps. But first I'm going to tell you there's two basic types of geologic maps that people make. They usually make either surficial or they make bedrock maps. Now, surficial geologic maps, there's a difference between the two, especially in the Midwest, like in Illinois, where basically anything older than Quaternary is considered bedrock, even though you can go to western and southern Illinois to some of the Pennsylvania deposits, and they're so soft you can dig them out with your hand. But and generally throughout the Midwest, that's what's considered surficials, Quaternary and younger. Okay, so I am going to talk about topographic maps. I'm not going to get into great detail on them, but first I need to kind of zoom out, give you the big picture. Here they are. Okay, these two maps right here. This map and this map are both Robinson projections. Okay, now here's some information on the Robinson projection below. This is from Wikipedia, and there's a link. It mentions a different projection in here. But the reason why I'm showing you this is because you notice that on lines of latitude, they're pretty much horizontal. It's an even division. Longitude, I mean, if you were to put this on a sphere on a globe, I wish I had a globe, but I don't. You can tell that the lines of longitude narrow as you get near the poles. Now, that's important in mapping in general because you have basically, for scale and for reference, you as you get towards the poles, the maps can get narrower, and there's one scale in particular that we use called the 7.5 minute quadrangle that we use in the continental United States that is perfect size for mapping. Well, I just mentioned a scale. What do I mean by that? Well, basically a scale on a map is usually written as a ratio. It'll be 1 to something. 1 to 24,000, 1 to 500,000, 1 to where are ya? 1 to 100,000. Okay. A lot of maps will have what's just called a verbal scale, like 1 inch equals, 10,000 feet. There's a problem with that. If you're making a map and you don't have any sort of scale at all, just a verbal scale like that, what if someone goes to print that map out that's smaller, or there's just a section or something, you don't know what's what. And even if you don't have, most geologic maps and topo maps will have bar scales. Okay, and that's good because that means no matter what size you print the thing out at, you're going to be able to figure out the distance. But even if you don't have that, you just have the ratio. Sometimes it's written like this is 1 to 100,000. Sometimes it's written as a fraction because what that means is 1 unit on the map is equal to 100,000 units on the ground. Okay, so it's a fraction. Some people write it as a fraction. But that fraction that people, or ratio, if you will, that people write it in, you can figure out, even if there's no bar scale, you can figure out on the map your distance if you really need to. And that ratio, like 1 to 100,000, If you wrote that as a fraction, that would be a very small fraction, okay, 1 to 100,000. So that would be a small scale map, even though it includes a much larger area. A smaller fraction like this is a 7.5 minute quadrangle topo map, which is at 1 to 24,000. That would be a large scale map. And these are ideal for geologic mapping. And if they're printed to scale, as this one is, this is an actual topo map from the USGS, 1 inch is equal to 2,000 feet exactly. There's no decimals or fractions past that. That's an exact measurement, and that's one of the reasons why I still use imperial as opposed to metric when I'm mapping. But this one is the Romeoville Quadrangle in northeastern Illinois. And it was one of the first geologic maps I ever made. You can kind of see it here in the corner. Obviously, I don't have a large scale printer to print it out full size, but that's the geomap of this topo map. When we make these geologic maps, we'll usually use a topographic map as a base, okay? And these are all available online from the USGS. If you just Google USGS Topo Map Locator Downloader, you can get these online for free now. Problem is, and as it was of today, the site likes to be down for maintenance a lot. So, but that aside, the new maps, you see these pink areas here. This is urban area development. These are big buildings, these black areas. This is, the blue is water. In this case, it's river valleys and small lakes. But on the new maps, you can do layers. Like you can get rid of the cities. You can get rid of the vegetation, which is green. I always leave the waterways on because you need them as landmarks when you get into cross sections, which I'll get into in a minute. But every geologic map must have 6 things. All right. I'm going to pull this little Romeoville one out. And I'm going to show you. I actually have it. Now, most geologic maps are 1 page. This one's actually 2. I generally make them as 2 because I make them on Publisher, and in order to conserve memory, I'll do them on 2 pages. But up here, you see we have the title with the authors and the year it was made. You need that on your geologic map, okay? You need a location. I do the whole state, or if I'm doing Ontario, I won't do the whole province usually because it's huge. But I have right here an approximate location. Okay, you need your legend. Okay, now the legend consists of several parts. Okay, these are geologic units over here, and these are my geologic map explanation. Now these are actually standardized symbols, but for mapping purposes sometimes you have to deviate from them or alter them slightly in order for them to be legible or understandable. So you always have to have those. Now you want a detailed description of your geologic units as well. I didn't put them on the first page. They are on the second page. Okay. So you have your title, you have your legend, you have your location. Now you need your scale, okay? But real quick before I get into that, when you do your geologic legend, like in this case, you'll see that there's letters abbreviating formations, which correspond to the colors here. The colors here correspond to the colors over here. The letters are included on top because sometimes if it's something like this that's really tiny, you can't really write out like Henry Formation across that. It's easier just to put like QH, all right? But you explained it over here anyway. But scale. Now at the bottom here, see, I have the scale. All right, which is exactly the same as the scale at the base of the topo map, but there's something else important on here that every map must absolutely have, and that is a north arrow. Okay, I put magnetic declination from the time I make the map. Now, what's magnetic declination? Well, it's where a compass points from true north. The magnetic north pole, oh hi Blackie, is never or almost never aligned to true north, and it drifts literally daily. And after a couple of years, it really can drift and throw your compass off. But there is a site called, if you Google NOAA, magnetic declination, put in your GPS coordinates to the area, it'll give you that deviation. So we have that useful tool now. These are my, in case you're wondering, these are my map cases for back in the day before we had things like GPS and easily accessible Google on our phones and stuff. 2-inch PVC, top cap, bottom cap, waterproof. Blackie's assisting by rubbing on my books and knocking them over, aren't you, buddy? Aren't you, buddy? Okay, so back to the map really quick. Another thing everyone needs, when you make maps like this is nice because it shows the Surficial Geology. This is a Surficial Geologic map. There is bedrock on it, but that's because it's exposed. If you look, where is it? It's hard to see, and I apologize for that. But if you look here, you see this letter with a line with another letter. That's a cross-section line, in this case A to A prime. We always label cross-sections A to A prime, B to B prime, C to C prime, etc., etc. And a map can have as many as you want. But what that does, what that cross-section does, is if you take this, and I'm going to fold it along the cross-section line, it gives you a slice through the earth at that line. Okay, so you have your surface, then you have a subsurface extrapolation, which in Illinois everything's pretty much flat lying. So we do something called vertical exaggeration. Now, vertical exaggeration is a ratio, but 99.9999% of the time, it's a 1 to something ratio. Because almost no one changes the horizontal distance. That'll be equal to this distance. But in order to show geologic units, they will do a vertical exaggeration like I did here in order to highlight things that aren't thin or too thin at that scale. And this is a 20x, 20 times vertical exaggeration. Down here, there's no vertical exaggeration. Actually, yeah, there is. Oh, sorry, but this is only 5 times because I wanted to go deeper. There were some deep wells in there that gave us a lot of information. So, in a lot of maps, like that one back there, you have cross sections here. This is A to A prime behind the lighthouse, B to B prime. Now these cross sections, see if I can find them. Here's A to A prime, so it's long. I can't find B to B prime readily, so we'll just stick with A to A prime. Now, this has no vertical exaggeration, and it's not needed. You don't need vertical exaggeration in this case because the geology is, there's been a lot of tectonic activity, so basins and stuff like that, and faults, you don't need to vertically exaggerate to show anything. Everything's thick enough and orderly enough, and ideally that's what you want. So if you're in an area with a lot of rock deformation, you don't really need to vertically exaggerate. So cross sections are important to get an idea of subsurface geology. Well, how do we know the subsurface geology? Well, there's a couple of ways. Oh, now Ezra's here. Say hi, Ezzy. There's a couple of ways to figure out the subsurface geology. One way, in a very flat area like Illinois, like with what I did here, this is almost all due to well data. People put in groundwater wells, and they usually have cuttings, or they'll actually core it out. And a lot of state surveys have these cores and cuttings on file for regular view, so you can figure out what's what in the subsurface. And then we draw our map in accordance with that and doing that cross sections. In an area like here in northern Wisconsin and western UP, we mostly rely, I mean, there will be some wells, but you're not going to have any wells that go down 15,000 meters, okay? So what do? Well, we're in the field making these maps, we'll take measurements, and they're on here, called strike and dip. And this is a rant for another time, I'll actually do this for you and show you how it's done. Basically, use a Brunt compass, and what it does is it gives you the exact orientation of that rock in space at the present time, from north. Well, strike is simply the connection of 2 points of equal elevation. They can be 5 inches apart, they can be 5 miles apart, it doesn't matter. But that's what strike is by definition. 2 points, a line between 2 points of equal elevation. And dip is perpendicular downslope to that. So you see I kind of drew a T with my hands. Well, that's what the map symbol looks like. It's kind of like a squat T. You'll have your line of strike, which you don't need to do anything with except orient it to north on your map, okay? And then the dip, well, obviously you can't draw the dip into the map, so what you do is you just draw the little dip symbol perpendicular to the strike, and you put the number of degrees under it. And from that, if you have enough of those, you can get a sense of how the rocks go into the subsurface, and you can generate cross sections like that. Okay, so I'm going to show you another geologic map in detail, and I'm going to point out things on here and how they have things and why they're necessary. This is the Geology of Sauk County, Wisconsin. The Wisconsin Natural History Survey and Geological Survey makes a lot of county scale maps, okay? They make some quadrangle maps, but they're far and in between. Quadrangles, like I said, are good size for most geologic formations, and the 7.5 minute quadrangle is really the size you want to use if you want to do detailed mapping without being too detailed. There's no point making a map to a 1 to 500 scale. It's just pointless. It's not going to show anything. You're zooming in too much. But this is further out. This is like a county scale. They have the location of the county in Wisconsin right here. And I'm showing you this one because every geologist in the Midwest, the United States, goes to this place, the Baraboo Incline, when they go on their structural geology field trip and sometimes on the sedimentology field trip. Everyone has been there. So this map shows you have your units over here, your location, your scale. This is a 1 to 100,000 scale. Okay, you have your bar scale here, you have your explanation with units. There's more units over here, but my easel isn't wide enough, so it's not really necessary for explanation, but it starts here. You always want to start youngest and go down your oldest. There is no standard for where to place these things on the map, because usually on a map you're trying to conserve space. You don't want too many open spaces. You also don't want everything so clustered together you can't read it. So there's no standard there, okay? Now this map has your symbols here, and another thing you really need on geologic maps are references, and they have some down here and down here. Unless you're north of James Bay in Ontario, I guarantee you somebody in the area you're mapping has done some work in the past, okay? So you need to reference that in there. Here, like on my maps, I'll put pictures. It's not a requirement. I only put pictures on my map if it shows something geologically unique that would be too wordy to write, okay? And then also on my maps, I put what we call part of the map report. If the map like this is really complicated, that report will be a separate document, because you can't just write 20 pages of text on a map, no matter how small your font is. But my maps, they're generally quadrangle maps, so it generally fits on there pretty nicely. So I actually put it on the map, and like I said, with pictures are not a requirement, but some people do and some people don't. Some people add other things too, like this up here. This is the county over here, and it shows you the Baraboo Hills, which is purple here. Okay, it shows you the Green Bay Lobe, and what the Green Bay Lobe was an ice sheet. This county begins from here west, begins what we call the driftless area, and here it's mapped. It forms a triangle from basically in Illinois, like here's Wisconsin, from like down here to up here. Glaciers never touched it. We don't know why. Now there are glacial deposits. There'll be lake deposits out in front of glaciers and outwash stuff like that, but there's no till. Okay, so it's driftless. This pink is the end moraine that the Green Bay Lobe left. And these are what we think were lakes during the time that Green Lobe base sat and deposited that moraine. But the Baraboo Hills are unique because when you start going north from, say, Chicago, this is really where the Precambrian starts to outcrop. That's why everyone in the Midwest goes here. And it's a nice textbook syncline. That's all I'm going to say about it right now. But it's a little more complicated than that. So like I said, this is a county map. Now, if you notice here, remember how I said north? You always want to put north on your map, a north arrow. There's no north arrow here. Why is there no north arrow? Well, they do tell you which way is north, they just don't use an arrow. If you look here, you'll see Township Range, which is an American system in the Midwest. I won't get into any more of that. But you have longitude and latitude up here too. And why do they have longitude and latitude and no north arrow? Well, because when you're working at this kind of scale, 1 to 100,000, what happens is north is not north all over the map. Okay, because I'm just going to move it over a little bit. Okay, when you're working with such a small scale as 1 to 100,000, what I meant by north is not north is that if you're standing here, true north is going to be like this way. If you're standing here, it's going to be this way. If you're standing over here, it's going to be this way. There's no set. I can't say, like on a large scale map, like 1 to 24,000 quadrangle, you're dealing with an area like this. So you can put a north arrow. It's not going to matter. It's not going to deviate from the map. But on a scale as small as this, it's such a large area that north is going to kind of swing back and forth because the Earth is a sphere. So that's why there's no north arrow here. But like I said, the easy way around that is put lines of longitude and latitude in, which they did. The USGS topo maps at the 1 to 24,000 scale will do that as well. Alright, now to get into the meat of a geologic map. Look at all these colors. What are these? Alright, these colors represent geologic units at the scale at which you're mapping. The formation is the basic geologic unit. Some formations are thick, like the Baraboo quartzite is over 1 mile thick. For you metric people, that would be like almost 2 kilometers, kilometer 2/3, something like that. Other formations are extremely thin, especially where they're flat lying. Like you go into Illinois, you'll have formations that are, 30 feet thick, 50 feet thick, which would be 30 meters. 30 feet would be 20 meters, about. So, you get thinner units because you can see more. It's easier to delineate it that way. So the formation just has to be a mappable unit. That's like the definition. Well, Blackie Dart. But if you're using such a small scale, you may have to group formations together. And some formations, the unit above a formation is called a group. And not all formations are part of groups. Not all groups are divided into many formations. It gets complicated, but that's a talk for another time. The important thing to remember is that all these colors represent different geologic units, okay, at the scale that this map was made. Pretty much all this purple is pretty much all the Baraboo quartzite or Baraboo formation. Like I said, it's a really thick one. So these colors with the letters, like here you have the Cambrian symbol, which is a C with a line through it, W. Now, I just happen to know that's the Cambrian Wanawak Formation, just because I've seen it so many times. And so that, and that color, that light tan, if you will, does correspond. CW, Wanawak, and Eau Claire formations, Ironton member, and with the Ironton member. So they did do some combining here. Now the CW, there's no standard. You can, that C is just Cambrian, the W they use for Wanawak, but they put other formations in there as well. And that's fine. You can do that as long as you explain it in your legend, probably because they weren't all mappable at this scale, and that's fine. So I'm trying to find some. I'm looking for something in particular. If I don't find it, I won't trail off too long. All right, I can't find it. So all these colors represent different geologic units. There is a standard by the USGS for using colors of certain times, like pretty much anything or quaternary is going to be a shade of yellow. A lot of people don't follow that, including myself, especially if you have a lot of units that are around the same time, as often happens with some glacial units, which aren't here. Like I said, this driftless area. Here's some, the tills. So with like all the glacial units, I mean, they're pretty close to each other, but the problem is if you have like 10 or 15 quaternary units, it's not practical on the map to have 10 to 15 shades of yellow. No one will be able to tell anything. So you can vary from that color. You can deviate from that color scheme. That's fine. I do it all the time. But here you can see, even just by looking at the map, the colors are somewhat standardized. You can tell that there's greens and blues here, so you can tell that these deposits might be related. This is a really odd blue. This olive colors and browns all are around each other. The reds tend to follow valleys. So even without looking at the legend, you can discern some stuff about the map, and this really stands out, the Baraboo Hills. So you can still look at it and gather some information just by looking at a geologic map if you know how to read it. Most of the units here, except for the Baraboo Hills, are flat-lying. They don't have any cross-sections on this map. Wisconsin does sometimes, like La Crosse County has them, but this one does not. They will have faults on here with relative movements. And like I said, I can tell this is a fault for several reasons. It has a U and a D. Now the standard universal symbol for fault is actually a solid dark line, but here it's dashed. That's fine. It's easier to read like that. It stands out, but they tell you what it is down here. So so you just got to keep referring to the legend if you don't know. Well, all the colors, no matter where they are, all the geologic units are all surrounded by lines on the outside. That's your contact. That's very important. You need to know where your contact is, and it's represented by a solid black line. I don't know anyone who ever deviates from that. Now, an approximate contact is usually a dashed thin line. And, well, what's an approximate contact? Well, if you strongly suspect, based on regional evidence, that a geologic unit is present in the subsurface, but you don't have any wells or any outcrops to verify that, exactly where it goes, you just put a dashed line. But that is basically how you read an actual geologic map. Like I said, most geologic maps use a topo map as their base, so you'll see a lot of things on there, like streets, named rivers, and those are important too when you're generating your cross section, because if you generate a cross section, you want, even if it's like from here to here, it says A to A prime, you still want to include things as you cross, like as your cross section goes. You cross a major river, you put an arrow. Oh, I cross that river. Oh, this is a major road. I cross that road. Or oh, I got a big lake here. I cross that lake. and down to the river, the end of the river, with the name of the river and an arrow pointing to it. It's just what you do. It helps people get their bearings a lot easier in a cross section, especially if your cross section, and they almost never, I mean, you're never going to plop a cross section right across here. It's always going to be down or over here and rotated or something like that. So adding those landmarks really helps when you do your cross section. Okay, before I wrap it up here, oh hi Blackie. Blackie looks like he's going to be assisting me during these Geo-File talks. He, like me, is also obsessed with copper. But before I wrap it up, I just want to sit there and talk a little bit in general. I was actually going to show some slides interjected in the video, and I decided not to do that. I actually tried doing it yesterday, but I decided not to do that because you would just see a slide and then I'd talk about it for like 5 minutes and nothing would happen. It was just me droning. It looked boring to me, plus I couldn't point things out. So I decided to not use slides in this series. I'm going to use printed stuff. I got an easel now and a black cat to help me. If you have any suggestions and or any topics of future episodes, please let me know. He's gonna knock that down. But please remember, this is a more technical series. I will continue to do my geo rants for less technical stuff. If you want, go ahead, like, subscribe. I'm not gonna beg you for that. But if you do, thank you in advance. Oh, black cat hair in an orange folder. What is it with black cats and orange? No wonder that's Halloween colors. But anyway, I just want to say thank you for watching, and Blackie, he thinks you as well when he's not licking himself. But anyway, I hope you learned something.